Welcome to the presentation of the paper entitled Prediction of the Consolidation Delay in Blockchain-Based Application. I'm Andrea Marin from the University Ca' Foscari of Venice, and this paper is co-authored by Simonetta Balsamo from the same university, Mitrani from the University of Newcastle, and Nicola Rebagliati who is a blockchain analyst. So this is my talk overview and introduction and contribution. So let's first of all recap the information that we probably all know about the blockchains. So blockchains are distributed ledger for storing permanent and unmodifiable data. They're usually associated with cryptocurrencies like Bitcoin or Ethereum and so on. But they may even not be necessarily associated with a cryptocurrency. There are several ways for guaranteeing data integrity in blockchains. We will consider the proof of work system that we will describe later. Data in blockchains are encoded in transactions, and the transactions are grouped into blocks. The blocks are validated and consolidated by special users, which are called miners. And once a block is created, the transactions containing that block cannot be modified anymore. So this is the sketch of a proof of work mechanism. The gray blocks that you see here are the consolidated blocks, so it's the actual blockchain, and all the miners try to add a block to the blockchain. The miners pick the transaction to add in the candidate block from their mempool, and the mempool is basically a priority queue. We will see later in details how it works. They pick the transaction from the mempool, they try to mine the block, and after validating the transaction, they have to solve a puzzle. So they have to perform a computation, which is usually consisting of some hash computation, and when they succeed, they have consolidated the block, and this block can be added to the blockchain and will be validated by all the other miners. How are the transactions chosen from the mempool? The protocol doesn't say the order of service, so it's not the first come, first served or anything like that. So in general, the miners choose the transaction that offer the highest fee per byte, and so they can increase, they can maximize their profit. Notice that the throughput of the blockchain has a limit, and this is given by the expected delay between one block generation and the other, for example, 10 minutes in Bitcoin, and the maximum block size, for example, 1 megabyte in Bitcoin. Another problem of deciding how one should offer for the transaction is given by the fact that there is a high variability in the arrival process in for example, Bitcoin blockchain. And clearly, when you are in this phase here, where the arrival rate is low, you can have a quick storage of a transaction, even offering a low fee. When you are in heavy load, like when we are here, then in this case, you must offer a high fee per byte if you are in a hurry to store the transaction. So the problem statement is this: given the situation of the blockchain, the conditions of the blockchain, is it possible to determine the expected transaction consolidation time given an offer fee? And if we have a model that allows us to support this decision, we may implement it in application, and the QE model can support the application to decide which is going to be the optimal fee, which will be high. For example, if a transaction is delay sensitive, but it can be low if the transaction is delay insensitive. So based on the timing needs that you have for storing the transaction, you can offer the appropriate fee. And so you don't waste money in the process of storing data in the blockchain. The contribution is the introduction of a QE model that analyzes the mempool and the delay of the transaction in the mempool based on the priority that they have on the fee that they offer. And then we study two methods for handling the case in which the arrival intensity is higher than the maximum throughput of the system. So in that case, we need to drop some of the transaction. And we will see two methods of dropping, one based on the maximum size of the mempool and one based on the timeout. Then we validate the model with the data retrieved from the Bitcoin blockchain. So the queue model is basically an MMB queue. So it's a queue with Poisson arrival, exponential service time, and a batch service with size B. And it has multiple priorities. The priorities go from 1, which is the highest priority, to higher numbers, and these are strong priorities, which decreases when the number becomes higher. When we have to form a block, we pick all the transactions that we can from the highest priority. If there is still free space, we go to the next priority. If there is still free space, we go even to the next priority, and so forth and so forth. So the same block can contain transaction with different priorities. One important thing is that since solving the puzzle of the block is a memoryless process, whenever you have a transaction with high fees that arrives, you can replace a transaction that you have here that offers less than the new one and kick it out, put it back to the mempool, and replace it with the new one that has just arrived. This is a very important feature of our model that distinguishes it from previous words. So the stability condition, the total arrival rate seen by class I, which is given by its own arrival rate plus all the arrival rates of the transaction with higher priority, must be lower than the maximum throughput of the system. For the unstable classes, we started two types of reneging policy. One is based on an exponential random time with rate gamma I for class I per transaction dropped, and the second one, we assume that the mempool has a finite capacity. Okay, so the solution of the queue without priority is very well known in the literature. It has a geometric form, the stationary distribution. It's 1 minus z, z to the power of n, and but z, instead of being like in the MM1Q lambda over mu, it's the real root of this polynomial. And we can prove that if the Q is stable, then Z1 is a root which stands between 0 and 1, and it's real. Once we have Z1, numerically solving the root of this polynomial, we can derive the expected performance measure for the highest priority class, like in the MM1Q. For the classes with lower priority without reneging, we can actually lump the classes from priority 1 to I, and so we aggregate the arrival process and we study the queue with that aggregated arrival process. And this gives the solution for the system with those classes. For when we have reneging, the expected space in a batch seen by a job of the lowest priority class can be found in this way. You got like this is the expected number of free batches in the free slots in the batch, okay? And this is given by this equation here. And then we approximate the batch service with single service rate with rate mu b. Okay, the approximation is good in a heavy load, but it decreases when the load is low. However, since we have reneging and we are interested in the reneging mechanism, we can assume that the load factor is high. So once we have this, we give a recursive scheme to approximate the probability of dropping in case of timeout. The case instead of the mempool with a fixed size, it's studied like an MM1K system whose solution is known from the literature. So the numerical validation of the model, the methodology, we validate our model considering the Bitcoin blockchain. We collect data from blocks in time intervals of 7 hours, And then for each transaction, we check the first seeing field taken from blockchain.com and bitaps.com. And then we cluster the transaction into 5 classes based on their fee per byte offered. Then we measure the expected consolidation time based on the data contained in the blockchain, and the intensity of the arrival process for the time interval that we observed is given by the analysis of the mempool in a BTC node. So these are the classes that we obtain. We can see from this data that the offered fee changes according to the load. In heavy load, for instance, the percentage of transaction that offers a very low fee is lower than in the case of moderate load. And this is actually what one expects from the analysis of the system. So this is the comparison of the result obtained by simulation, model, and the measurements. And you may see that the accuracy of the model is very good. This is the distribution of the response time in case of, this is simulated, in case of heavy and moderate load. We can see that class 1 and class 2 don't feel much the passage from heavy load from moderate load to heavy load, but when we go to class 3, class 4, and class 5, the response time becomes much worse. This is the analysis of the reneging policy, and we may see here that since we introduce an approximation, there is a gap in low load between what has been predicted by the model and the estimates of the simulation, but we knew that the accuracy of the approximation was somehow poor in low load. However, in heavy load, the accuracy of the approximation is very good. Another thing that we should observe here is that here we have the analysis of the consolidation probability when the reneging time is 72 hours, while here we have the reneging time of 48 hours. We can see that the two plots are not very different one from the other, but the case B requires a mempool which is much higher than that of case D. And hence, we are investing more resources of the miner, but we don't gain benefits in terms of a higher consolidation probability. So the conclusion, we have presented the QM model for the analysis of the expected time of consolidation in blockchain based on proof of work. The application of this result allows software to automatically decide what should be the offered fee for a certain transaction given the working condition of the blockchain in a certain moment and the time requirement, the delay requirement for the transaction storage in the ledger. The validation of the model has been done with Bitcoin data and showed a good accuracy. And finally, we studied 2 different types of reneging mechanism in the case of overloading system, one based on timeouts and one based on finite capacity mempool. As future work, we would like to develop a transient model that takes into account also the state of the mempool at the moment of the transaction creation. At this moment, we are working in steady state, and so the state of the queue when the transaction is created is not important for the results, but in fact, in practice, this is an information that may be available to the application that is taking the decision, and it may improve the accuracy of the prediction. Thank you very much for your attention.